Hello. Good morning, afternoon, or evening, depending on where in the world you are joining us. My name is Louis Wagasback, and I'm the Applications Laboratory Manager for TA Instruments. On behalf of TA Instruments, I'd like to welcome you and thank you for joining us in this webinar series. Today is day one of a 5-day material science webinar series. Today's speaker is Dr. Terry Chen. Dr. Chen is Senior Application Scientist with TA Instruments. She received her PhD in Polymer Science from Sun Yat-sen University in China, where she specialized in polymer synthesis and engineering. She did her postdoc research and later became a research assistant professor at University of Maryland. During that time, her research was focused on biopolymer modifications and characterizations. Dr. Chen joined TA Instruments in 2004. Her key responsibilities include customer support, consultation, and teaching customer training courses. Dr. Chen has more than 50 publications in peer-reviewed journals and 2 U.S. patents. The title of Terry's webinar today is Thermal, Rheological, and Mechanical Characterization of Thermosets. During the webinar, you can submit questions, and after the talk, we will answer as many as we can. With that, I'm going to hand it off to Terry. Terry?
Hi. Hello, everyone. Louis, thank you very much for your introduction. Everyone, thank you very much for attending our today's webinar. My name is Terry Chen. Our today's webinar topic is on thermal, rheological, and mechanical characterizations of thermosets. Here is what we would like to cover for today. First of all, we would like to give a short introduction of thermosetting polymeric materials and their applications. Then we'll be spending more time focused on discuss some of the commonly used characterization techniques that are used in thermosetting polymer industries. Specifically, we will introduce the applications of thermal analysis instruments such as DSC, TGA, rheological instruments, and also dynamic mechanical analysis instruments. Thermosetting materials are high-performance, cross-linked polymeric materials. Unlike thermoplastic polymers, thermosets are polymers that are irreversibly hardened by curing from a liquid or soft solids. So upon reheat, a thermoset cannot be melted for reshaping. Examples for thermosetting materials include epoxies, cross-linked polyurethanes and polyesters, and filled vulcanized rubber elastomers, or some of those formaldehyde foams. Because of its unique characteristics, thermosetting materials has been widely used in varieties of industries, especially in electronics, automotive, and aerospace. So if you simply do a Google search, you'll be surprised to find out that actually over 50% of the materials used in aerospace industries are polymer composites, and most of them are actually thermosetting polymer composites, because this kind of materials exhibit excellent mechanical properties. They are cheaper in price, and also they have lighter weight. So this can help to reduce the usage of metal. In addition to excellent mechanical properties, thermosetting materials also have good thermal stability, ideal electronic properties, good solvent resistance, and also fire resistance. This diagram summarizes the mechanical reactions of a thermoset curing. So basically, the material starts from small molecules or short-chain oligomers in a liquid form. By adding a cross-linking initiator, the reaction starts. And then the system starts to build up the molecular weight. It goes from small molecules to large molecules, from oligomers to polymers, and then to highly branched polymers. At the critical time when the first cross-linking network is created, the system forms a gel and completely loses flowability. This is the point when people typically call it as a gelation. After the gelation, the cross-linking reaction still continues, and the material undergoes a vitrification and still builds up its mechanical strength until eventually it forms a hard solid. This phase transition process can be described using this time temperature transformation diagram, which people call that the TTT diagram. Since the performance of thermosetting material is strongly influenced by the base polymer architecture, processing conditions, and filler compositions, appropriate characterization techniques becomes critical in thermoset product development. Over the years, many analytical tools have been used in thermoset industries, from lab-based formulation and development to processing and manufacturing. In our today's talk, I would like to specifically introduce the applications of using thermal, rheological, and mechanical techniques in thermoset analysis. First of all, I would like to discuss the use of differential scanning calorimetry, which people call that DSC. DSC is a very popularly used thermal analysis instrument. It measures the amount of heat that flows into or out of a sample as a function of time. Temperature as a function of time, temperature, or a certain environment. The heat flow transition can represent a chemical reaction such as curing, or a physical structural changes such as crystallization or crystal melt. Specifically for study the thermoset curing, DSC can be used to measure the heat of reactions, to estimate the percentage of curing, measure glass transition, and the heat capacity change. Cross-linking reactions are exothermic. As the sample cures, it is almost always accompanied by releasing of heat. Therefore, in a DSC temperature scan, curing reactions shows an exothermic peak in the heat flow curve. By integrate the area in the peak, we can calculate the curing enthalpy. This enthalpy can be used to quantitatively measure the degree of curing. Here is the equation. Here is the equation of calculating percentage of curing after 10 hours of a reaction at ambient temperature of a epoxy thermosets. So the percentage of curing equals to the enthalpy of an uncured material minus the enthalpy of the sample after cure for 10 hours, and then divided by the uncured sample enthalpy. So from this results, we can see that for this particular epoxy sample, after 10 hours of curing at room temperature, it is only cured for about 34%. In addition to measure curing enthalpy, a DSC test can also be used to measure glass transition of this material. Glass transition usually shows a step in the DSC heat flow curve. Here's a case study of using DSC to monitor a curing process of a epoxy plus Jeffamine D230 system. This sample is kindly provided by Huntsman Corporation, and we really appreciate that. Thank you. Jeffamine is a slow-curing cross-linking agent at ambient temperatures. As you can see from these results, when the sample gets more and more cured with time, the curing enthalpy is decreased. In the meantime, the glass transition of the sample is shifting to higher and higher temperatures. From this measurement results, we can then calculate and plot the percentage of curing as a function of time. This allows us to be able to predict the time to reach a certain curing stage. Also, we can plot the shift of glass transition as a function of curing. All of these results provide useful guidance to engineers and chemists who design the formulation and process this kind of epoxy material. Many times when you perform a traditional DSC measurements, for example, a heat-cool heat measurements on a thermoset materials, right at the glass transition temperature, you will see this kind of sharp endothermic peak. This endothermic heat flow is associated with the enthalpic recovery of the material. However, since this enthalpic recovery always occurred right at the glass transition, it makes it difficult to accurately determine the glass transition temperature. One useful technique in DSC analysis to address this kind of issue is called the modulated DSC. Instead of conducting a linear heating rate in the test, you can program the heat temperature with a sinusoidal waveform at a certain frequency and amplitude. This modulated DSC technique is capable of separating the heat flow signals between the heat capacity and heat kinetic related activities. The heat capacity related signals include heat capacity, glass transition, and most of the melting. In the test results, these kind of signals are defined as the reversing heat flow. The kinetic-related heat flow signals include enthalpic recovery, evaporation, crystallization, curing, denaturization and decomposition, and also part of melting. So in the test results, these part of signals are defined as the non-reversing heat flow. So if any of you who are interested in getting to know more about this modulated DSC technique and applications, and please consider to take one of TA Instruments offered DSC training courses. Here, specifically talking about using this technique to solve the problem to measure thermosetting materials. So we can see that, okay, by using modulated DSC technique, we can successfully separate this enthalpic recovery signal into the non-reversing heat flow curve. And then the glass transition is now able to be accurately measured from the reversing heat flow signal. DSC analysis is also used to study the kinetics of curing reaction. Here, I'm going to list some of those most commonly used kinetic analysis models. The simplest kinetic model people usually use is called the Bochart-Daniel model, which is described in ASTM E2041. This method is only using one single heating rate data to calculate the reaction order and activation energy. So it is fairly easy and quick. This method works reasonably well with some simple first-order reaction system. The other kinetic method is by conducting a series of isothermal curing tests at different temperatures. This isothermal kinetic approach is good to use for the nth-order reactions, and also it is good for auto-catalyzed enthalpic systems. The third kinetic model is the multiple rate method. Sometimes people also simply call it like Ozawa method, which is described in ASTM E698. This method is based on a series of temperature ramp experiments with different heating rate. Here, I would like to show you an example of kinetic studies on this epoxy jet foaming curing system using this multiple rate kinetic model. Basically, I prepared a series of DSC samples with almost about the same mass. Then I load them to a DSC and started the temperature ramp experiment with different heating rate at 1 degree, 3 degree, 5, 10, and 20 degrees per minute heating rate. From these test results, we can then plot the log heating rate versus the inverse of the peak temperatures from the results. As you can see that they follows a reasonably good linear relationship. And then from these results, we can calculate the activation energy and the other kinetic parameters. TA Instruments thermal analysis software provide a kinetic analysis package which allow users to be able to fit their experimental results to those commonly used kinetic models. Here is just a demonstration of automatic kinetic analysis using this ASTM E698. So through this kinetic analysis, it helps people to be able to predict or estimate the percentage of curing over time at different curing temperatures, or the time to reach a certain percentage of curing at different temperature. The other thermal analysis instruments I would like to introduce and discuss today is the thermogravimetric analysis. So people also call that the TGA instrument. The fundamental application of this instrument is to study the thermal stability of a sample. Actually, for all users who need to design an appropriate DSC heat-cool heat experiment, they should all be doing a pre-temperature scan on the TGA first. Make sure the sample is stable at the highest temperature they will run their DSC. This is important to protect their DSC furnace from being contaminated from sample decomposition. In addition to study thermal stability, a TGA instrument is also used to measure sample oxidative stability, measure compositions of polymer composites, moisture content, study polymer decomposition kinetics, and also estimate the lifetime of a product. The TGA hyphenated technology can be used to perform the evolved gas analysis and evaluate safety of thermal decomposition. When polymer burns, it may release gases that are toxic to people. So the evolved gas analysis is critical for a safety evaluation of using this material at elevated temperatures. The hyphenated techniques that are used in this application include TGA with mass spec, TGA with FTIR. Sometimes when polymer burns, multiple fractions of gases may come out at the same decomposition temperature. So in this case, a combination of TGA, GC, and mass spec technique can be used. So we let the evolved gas pass through the GC column first to separate, and then we use the mass spec for the analysis. Okay, here's a case study that one of my colleagues did on a field crosslinking rubber elastomer. From the TGA analysis, it shows that this rubber contains about 20% carbon black and roughly about 25% inorganic silica fillers. For the evolved gas analysis, he first connected the TGA with an FTIR. From this table on the right side shows that all the small molecules that are coming out at different decomposition temperatures. The next test he did was to connect the TGA with a GC and then with a mass spec system. So the table here on the right side shows the measured results at decomposition temperature of 210 degrees C. When the evolved gas passed through the GC column, all fractions of small molecules can be successfully separated and then being further analyzed by the mass spec. If any one of you who are interested in this technology and wanted to read more, please feel free to go to TA Instruments website and download our applications note paper with the number labeled as TA 416. In addition to thermal analysis techniques, rheology technique is also important to thermoset polymer research and manufacturing. Rheology measures viscosity and viscoelasticity of a material as a function of time, temperature, shear, or frequency. For the research work on uncured resin or formulation, the viscosity measurement in rheology can help to evaluate the workability, pourability of the resin at some coating shear conditions. It helps also with optimizing the processing temperature window. A rheological measurement can also be used to monitor the entire curing process. It can measure samples before curing the initial viscosity of the sample, and then track the changes of modulus throughout this entire curing. Rheological measurement can be used to measure the gelation and also being used to evaluate the mechanical strength of the end-use product. The most commonly used rheological experiment for thermoset analysis are conducted under oscillatory mode. In an oscillatory test, the instrument applies a sinusoidal stress to the sample and measures the sample's response. If this oscillatory amplitude is small enough and does not irreversibly break the structure of the sample, the responding sample signal should also be in a sinusoidal waveform. To monitor thermoset curing, this kind of oscillatory test can be performed at either isothermal conditions or with a specific programmed temperature profile. And the measurement results, the parameters, will present samples modulus, which include storage modulus, loss modulus, and also samples damping factor, elasticity, which defined as 10 delta, and also the complex viscosity. Here is the case study results of measuring a 60 millimeter epoxy throughout the curing at an isothermal temperature of 80 degrees C. So basically, the sample is loaded to a rheometer with a 25 millimeter diameter parallel plate. This has to be a disposable parallel plate. So from this result, you can see that at the very beginning, when you first loaded the sample has pretty low viscosity. It behaves like a honey, low viscosity liquid, where G double prime is greater than G prime. That means the sample behaves liquid-like. During this reaction, both moduli and viscosity are increasing sharply as a function of time. So at the time around 204 seconds, this sample undergoes a liquid to solid transition where G prime is equals to G double prime. Beyond this point, G prime start to take over, become higher than G double prime, that indicating the sample becomes more solid-like. So after the sample is fully cured, both moduli and the complex viscosity reach to a plateau. Again, from this results, as you can see that during this entire measurement, the sample's viscosity and moduli changes over like 5 to 6 decades. So that means to design an appropriate rheological test parameters in order to get good rheological measurement results becomes quite difficult and challenging. So if any one of you who are interested to learn more about how to properly design a good rheological experiment to monitor thermoset curing, then please refer to my conference proceeding paper that I published last year at SAMPE. Or if you could give me your email address, I'll be happy to also send you a copy of my paper. Not all curing is conducted under isothermal conditions. So actually, most of the time, people like to use the rheological measurement method to mimic a real manufacturing curing temperature profile. So here's an example to demonstrate a temperature ramp followed by an isothermal curing profile. Of course, you can also design some other more complicated profiles to monitor your curing. From these results, you can actually monitor to track changes of sample viscosity and modulus change throughout this entire temperature profile. At the beginning, your sample remains stable with temperature. So as you increase in temperature, both moduli and viscosity decrease when the temperature gets higher. And then up to a certain critical temperature, the whole thing reached to a minimum. So you are able to accurately measure minimum viscosity temperature. This is actually the highest operation temperature for processing an uncured resin without initiate curing. So after this temperature, curing starts, the reaction starts actually, and then both moduli and viscosity increase sharply with further increasing in temperature. And after that, you can see an obvious liquid to solid transition, which is the gelation. And then you can also measure at what temperature and what specific time the sample gets fully cured. The gel point in the thermoset reaction is a critical parameter. At this gel point, sample shear viscosity goes to infinity. System completely lose solubility. And the molecular weight of the sample goes to infinity as well. In general, people empirically like to use this G' and G" crossover point and define this as the gel point. However, many years ago, Professor Henning Winter has found out that using G crossover point to define gel point is not always correct. So it is only correct for some simple systems when the polymer relaxation follows a power law relationship with the N equals to 0.5. But for most of the curing systems, this is not always true because the measured gel point, the measured G crossover point, is frequency dependent, which means if I use 1 Hz for the measurement and you use 10 Hz for the measurement, we will be seeing a different gel point. So Professor Winter actually recommended a more precise way to describe a true gel point in the thermosetting system. In his method, he said you should be doing a whole series of tests with different measurement frequency. After the measurement, you can then plot tangent delta as a function of time, overlap all the test frequencies at different frequencies. The crossover, the 10 delta crossover point, is the true gel point of this system. This means you have to conduct multiple tests at different measurement temperatures. Multiple runs means multiple sample loading, multiple sample preparation, and also longer test. So then the question is it possible that we can actually use a simple, one single experiment to get all the information for multiple frequencies? The answer is yes. Actually, in the rheology analysis, there is a useful technique that is called multi-wave. This multi-wave function allows combining multiple frequency waveforms into one single waveform. So this is just like combining 3 separate frequency tests into one single test. So the figure on the right side actually shows a demonstration data of combining 3 test frequencies at 10, 50, and 100 radians per second, all into one single waveform, and then also into one single test. The total measurement time will be controlled by the fundamental, which is the lowest test frequency. Each frequency can also use its own strain amplitude, so that the total measurement amplitude will not be going over the linear viscoelastic region of your sample. As you can see from these results, at each particular time, 3 data points are generated simultaneously. Each data point represents data at 3 frequencies. Each point represents data at each frequencies. So then after the test is finished, you can split all the 3 frequency data, and the data on the right side shows the G crossover that measured at different test frequencies. So as you can see, the G crossover is not happening at the same time. The higher the test frequency, the G crossover will show up at the later time. Then from these results, we can overlay the test with plotting tangent delta as a function of time. The crossover point of the tangent delta is actually the true gel point of this epoxy system. In rheological analysis, we can also perform the gelation kinetic analysis. Gelation kinetics can be calculated using a series of isothermal rheological testing at different curing temperatures. Here, this is the demonstration of curing this thermoset epoxy at 50, 60, 80, and 100 degrees Celsius. After the test, you can then plot the log G crossover time and plot it against the inverse of curing temperature. And from these results, you can further use the Arrhenius model to calculate the activation energy of gelation. When polymer cures, they shrink and increase in density. The amount of shrinkage can cause trouble. They can cause cracking or delamination to the end product. Using the rheological measurement, we can actually monitor and quantitatively measure the amount of shrinkage. So most of the curing experiments on a rheometer are conducted using disposable parallel plates. So here I would like to introduce two ways to quantitatively monitor this curing shrinkage. The first method is, during the measurements, you hold the sample gap constant. And then, from the measurements, the instrument axial force transducer is able to actively recording how much force is built up throughout curing. So this result actually shows the shrinking force of this system built up almost as high as 15 Newton across a 20 millimeter diameter plate. The other method you can use is, to measure shrinkage is by actively adjust the instrument head to release the shrinking force. So if during the curing measurement, if you actively move the instrument head to release the force that's built up in the sample, then you can then use this method to measure how much the gap is changing during curing. In rheological measurements, instead of studying curing with a function of time or temperature, we can also study curing under different circumstances. This is a case study demonstrating using a rheometer to monitor UV curing with 5 different dental materials with different formulations. So using rheological measurements, we can quantitatively compare which formulation cures faster and how fast, and also which formulation will reach an ideal final sample modulus. TA Instruments Discovery Hybrid Rheometer is also equipped with a humidity chamber. This humidity chamber allows rheological measurements being able to conduct it with both temperature control and humidity control. Here is an example showing the measurement of a silicon caulk cured under different RH environment. This result certainly shows that, particularly for this caulk, it cures much faster with higher humidity environment. When thermosetting polymers are used in electronic industries, most of the time people are interested to find out their dielectric property of this material. On TA Instruments rheometers, we are able to attach a dielectric accessory to the rheometer so that it allows people to be able to perform a simultaneous rheology and dielectric measurements. And here is the results, showing the simultaneous measurements on a high-performance epoxy sample. During these measurements, the rheometer performs physical analysis measurements and reporting storage modulus, loss modulus, complex viscosity change as a function of curing time and curing temperature. In the meantime, the dielectric bridge simultaneously actively reporting the dielectric signals, and they reporting permittivities, capacitance, and conductance change at single or multiple dielectric frequencies. The last analytical technique I would like to discuss today is the dynamic mechanical analysis, which people call it the DMA. A DMA instrument measures the mechanical properties of a solid material. Specifically, it can measure samples' modulus, stiffness, damping or elasticity, glass transition, creep, or stress relaxation of a polymeric material. DMA is mainly used to evaluate the mechanical performance of an end product material. Many times when people use this DMA analytical instruments, there are always some confusions between DMA and rheology, also between DMA and thermal analysis. Since a DMA is mostly used to conduct temperature ramp experiment to measure samples' viscoelastic properties as a function of temperature. Therefore, people usually turn to consider a DMA as a thermal analysis instrument. And also, when people using a rheometer to conduct temperature ramp experiments, sometimes people call that a DMA test instead of saying, I'm doing a rheological test. So what are the differences between them? This diagram is actually provide a very good illustration on DMA and rheology measurement windows. So a rheometer is capable of doing temperature ramp experiment to measure viscoelastic property of samples with a wide range. It can measure sample from low viscosity liquid all the way to up to high stiffness solid. However, rheometer only conduct the measurements under shear deformation mode. Even when using a rheometer to measure a solid sample, it conducting the test in the torsional mode. So rheological measured modulus is defined as G, which is the shear modulus. Well, a DMA is capable of measure sample under linear deformation mode, such as tension, compression, or bending. It can handle samples with varieties of different shapes or forms, such as thin films, like rectangular bars, like tubular shapes, fibers, or like even for O-rings. But a DMA only measures sample in the solid states. So the measured modulus on DMA is defined as E. The relationship between E and G is described in this equation, where the nu here is the Poisson's ratio of the material. DMA is the most sensitive instrument for the measurement of polymer relaxations and transitions. It is more than 100 times sensitive compared to using a DSC regarding measure the glass transition of a highly cross-linked, especially highly cross-linked or highly filled thermoset system. In addition to glass transition measurement, a DMA is also a very sensitive instrument to measure all subambient transitions in the polymers, such as beta or gamma transitions. Those subambient transitions are associated with some local or side chain polymer relaxation. To measure this kind of transition, subambient transitions can help us to study the impact strength of this material. So how is cross-linking affect the glass transition temperature? Actually, we have already talked about this glass transition shift during the thermal analysis, DSC analysis. We were able to observe that when increasing cross-linking density, TG will shift to higher and higher temperatures. So the question is, like, how do we explain this from the molecular level? So during a curing reaction, as we increasing this cross-linking network, the sample increases its density. There are less and less free volumes between polymer chains. The molecular motion will become more and more restricted. So therefore, it needs to have more energy, higher temperature for a polymer chain to be able to relax and move. Therefore, you can see that the glass transition temperature is showing up at higher and higher temperatures. So from this slide, you can see the DMA measurement results. When increasing cross-linking density, TG is shifting to higher and higher temperatures. And also, the 10 delta peak density becomes lower, and the peak becomes wider. At low cross-linking density, the glass transition shift can be found to increase almost linearly with the number of crosslinks. But at higher cross-linking density, especially when we talk about highly cross-linked and also highly filled thermoset systems, the glass transition becomes really broad and weak and not easily being able to identify it using DSC technique. For a uncured thermosetting polymer, the cross-linking density can be quantitatively calculated using the DMA measurements. Here is the equation of how to calculate the molecular weight between cross-linking networks using the modulus measured at the rubbery plateau region. And then from here, we can quantify the polymer cross-linking density. Can we also use the DMA measurements to monitor residual curing? The answer is yes. For a thermoset system, if you load it onto a DMA and conduct a temperature ramp experiment, after the glass transition, if you actually observe an increase of storage modulus as a function of increasing temperature, and this is indicating for some residual curing. But unless you know the sample you're working with is really a thermoset, be careful of interpreting this kind of data, because for some linear polymers, partially crystallized linear polymers, this after TG, this kind of increase in storage modulus could also be due to some cold crystallization. As I have mentioned earlier, thermosetting polymers are mostly used with fillers. Adding fillers to polymer could, number one, lower the cost, and also it significantly enhances its mechanical strength from both below and also after the glass transition. Here is an example of using DMA to measure this epoxy composite with different amount of talc filler. From these measurements, we can quantitatively measure how much improvement we can achieve by adding certain percentage of talc. But a filler enhancement will not change the glass transition of the thermoset material. Here's the conclusion of our today's talk. Thermosets are widely used in a wide range of industries such as automotive or aerospace. The performance of thermoset material is strongly influenced by the base polymer architecture, processing conditions, and also filler composition. All characterization techniques that we outlined today provide useful tools for studying thermoset materials from different perspectives. Each technique provides complementary information for people to obtain better understanding on thermosetting materials. With that, I would like to end my today's talk. Thank you all for your time and attention, and I'll be very happy to answer some questions. Thank you.
Thank you, Terry, for that great presentation. So we're now going to start a question and answer session here where I'll read off some of the questions that were submitted in, and Terry will answer them. I will let you know that we had over 1,000 people sign up for this, so there are a lot of questions, and we won't be able to answer them all. But what we will do is later this week, we will answer the questions by email that we didn't get to. So you'll be receiving answers to those questions later this week. Also, people have asked about copies of this, etc. I'll let you know that the webinar will be archived and available later this week for replay. So it'll be available as a recording that you can replay at any time. And I encourage you to refer to the apps notes that are available in the resource section of the webinar and that are also available on our website. Now with that, I'm going to start asking some of the questions that have come in. So Terry, the first question is, I have a DSC 2500, but my sample cures so fast that I'm not able to see it. It cures within less than 5 minutes at ambient temperatures. How can I measure this curing on this type of sample?
Well, this is actually a great question because, as we all know, thermosetting material is not stable. From the moment we prepare them, they will start to react. If your sample is cured that fast, it's going to be really challenged for using both DSC or rheology instruments for the performance. The only suggestion I personally could provide it to you is you may have to consider prepare the sample and load the sample at lower temperatures. Like, for example, if you can refrigerator, put the sample in a refrigerator, cool it down, and also prepare and load the sample at low temperatures and conduct the measurement from there, that could be the best suggestion I can give you for that. Again, I understand this is a good question. Thermoset can cure really, really fast in certain temperatures and certain cases. So there's not much we can do unless we lower the sample preparation temperature. Thank you.
Thank you, Terry. All right, question number 2. I have a Q800 DMA. Can I use this instrument with the compression clamp to measure epoxy curing?
Well, the answer to this question is yes or no. In theory, if you are able to successfully load your sample to a compression clamp, and the instrument will conduct the measurement and give you some results. But personally, nobody will recommend you to do so. It's because DMA clamps are non-disposable. Okay, if you load your sample, let the sample cure between the clamps, that's going to be a really expensive test. So most of the thermosetting curing analysis are conducted using a rheometer with disposable plates. So I would highly recommend you consider use disposable plates on a rheometer to perform your curing analysis. DMA is not like you cannot do so, but the thing is just like if you ever glue the whole clamp together, you're not able to separate them. Thank you. That's it.
Okay, thank you. Next question. Now, this is kind of goes similar along with the last one, only on a rheometer, but I think it's a good question. How do you remove the cured sample from the rheometer?
That's a good question. How do I remove it? Since I mentioned that several times during the talk, it's just like, if your sample, is an elastomer, if it's a rubber elastomer, after the curing, you can successfully peel it off, you can use the standard geometry. But most of the measurement, are conducted using disposable plate. So TA Instruments rheometer, we always provide with customers the disposable parallel plate with different diameters. We have 20 millimeter diameter, 25 millimeter diameter, or even 8 millimeter diameter. So after the sample is cured between the plates, you can just simply take it off and throw it away. So if you don't know how hard your sample is, I would highly recommend you to first use the disposable plates for your measurements. Otherwise, once you glue things together, is a permanent thing. Thank you.
All right, thank you, Terry. Here's one on multi-wave. Is multi-wave functionality available on any rheometer?
Wonderful. This multi-wave functions is available on both TA Instruments Discovery Hybrid rheometers and also the Aries G2 rheometers. I have an applications note paper on this, and also one of my colleagues was planned. He submitted a paper to ANTEC. We were about to present this topic in ANTEC, but unfortunately it was canceled due to this coronavirus pandemic. But we do have an applications note. If you go to TA Instruments website, you should be able to find an applications paper on multi-wave functions, specifically discussed on both model of TA Instruments rheometers. If you don't find it, simply give us your email address, and I'll be more than happy to send you a copy.
All right, thank you. Looks like we got time for about 2 more. So the next one, why does crossover modulus value change with curing isothermal temperature? I understand that time will change, not sure why modulus crossover value changes.
That is because of your measurement frequency. Because, okay, the modulus measured at different frequencies is actually, the measured modulus actually correlates to the sample materials relaxation. The higher the measurement frequency, the sample actually relaxation will have more and more challenge to follow this oscillation. Therefore, okay, the sample behaves more stiffer, so the modulus will show higher. So that's why you will see that as you're using higher measurement frequencies, the modulus will show at higher values, and that's what you see from the measurement results.
All right, thank you, Terry. So last question here. When you measure your sample in the humidity chamber, do you have to worry about the diffusion rate?
Oh, that's a great question. The diffusion. I know there are numbers of people who are interested in this humidity measurements under humidity control, especially for measure some kind of like a caulk materials. You probably did not pay attention when I talk about this, introduce this humidity chamber. So it goes when we perform a humidity control measurement, we provide to our customers with different kind of specialized accessories. When I introduce the measurement for the caulk curing, the geometry I use is not parallel plate. The question you ask, I understand. If you load your sample between parallel plates, there will be a diffusion limitation from the edge of the parallel plate all to the center. Most cases you will see the edge gets cured, but the center still remains uncured because moisture cannot diffuse in. With this, the specific geometry I used is a annular ring geometry, which allows the humid air to be able to diffuse from both sides of the sample. So we actually have we did some presentation. We have some good posters regarding using this kind of special accessories. If you are interested, I'll be happy to share with you some more documents on this.
All right. Thank you very much, Terry. So remember, any questions that we didn't answer, we will answer later this week by email. I want to thank Terry for her excellent presentation and for the time for answering the questions. And I want to thank all of you for attending and your attention to this. Remember, join us tomorrow as Dr. Malin Sirkus gives a webinar titled Unlock a New Dimension in Your Battery Research Through Isothermal Microcalorimetry. Thank you, and we look forward to you joining us tomorrow and the rest of the week. Goodbye.
Thank you. Goodbye.